So, hey everybody, thanks for coming. My name's Finley Asher. I'm an aerospace engineer. I'm part of Safe Landing. We're a global community of aviation workers. We've got pilots, cabin crew, factory workers, aerospace engineers, air traffic controllers. I'm personally an aerospace engineer and have a background in aircraft engine design. Um, we want to reduce the climate impact of our sector. We want to understand the best way we can do that and how we can contribute to that happening from within the industry using our expertise and using the influence that we've got. Um, Part of that is we're really interested to look at what the future of aviation might be, what technologies and policies are more promising than others. So today we're going to focus specifically on sort of future aircraft technology. We've got Georgi Atanasov here from DLR, the German Aerospace Centre. We've had a previous presentation from Georgi before on the benefits of flying slower. And yeah, had a lot of interest last time. It was a really good technical presentation and discussion. So looking forward to that today. Just to give you a little bit of an agenda, I'm expecting Gorgy's presentation to be about 35, 40 minutes to begin with. And then we can spend maybe 20 minutes with Q&A up until the hour. Um, People are free to leave whenever you like. You might need to leave after the hour, but we're going to continue for an extra 30 minutes after there, where Gorgy's going to go into a bit even more technical detail with some additional slides, and we'll have a final Q&A after that before closing. So yeah, I'll pass over to Gorgi. Thanks for being here, and looking forward to your talk.
Yeah. Okay. Yeah. Thanks, Finley. Hello, everyone. My name is Georgi Atanasov from the DLR Institute of System Architectures in Aeronautics. For the past maybe 5-6 years, I've been in the middle of all kinds of projects exploring the potential of battery electric flight, and specifically in combination with plug-in hybrid systems. And I'm going to do a summary here with the most interesting results and insights on the topic. So let me share the slides. Okay. Okay, I hope everybody sees this.
Yeah, that
You
looks
see the
good.
slides. Okay, thank you for that. Yeah, so the session will be divided into more theoretical part on how battery electric aircraft can be designed. So starting with an introduction on the plug-in hybrid propulsion, of course, then the theoretical part, and including some equations and some basic rudimentary principles for calculating aircraft range. So I will be diving into some high level parameters on how we model aircraft. And then go into design strategy for battery electric aircraft and discuss what kind of aircraft utilization distance is used in the global aviation, and what is required for as range for such aircraft to be viable. And then go into this exact project result overview on the concept. And as Finley mentioned, there will be some pauses in between the different sections so that we can discuss them separately and not mix the questions up. Basically, topic by topic, discuss the presented content and then continue. Okay, so our overview on the plug-in hybrid electric propulsion. It is basically electric propellers or electric propulsors that are driving the aircraft, and they're powered primarily by batteries, so battery electric flight. So the aircraft can do a completely electric mission and service completely electric routes. And range is usually up to 300 to 600 kilometers, depending on the battery technology. And everything is done electrically. It's like taxi, takeoff, climb, cruise, descent, landing, and so on. Secondary power source are range extenders driven by, so generators driven by gas turbines serving as range extenders, and they serve mainly for operational flexibility. When additional range is required, and with their help, such an aircraft can achieve even thousands of kilometers of range, which is practically impossible as of today's view on battery technology for only battery electric aircraft. Maybe scratch the surface on 1,000 kilometers, but not too much. But with range extenders, that's operational flexibility is not a problem. And these range extenders are also used for mission reserves. So plug-in hybrid, like in cars, the term is from the car technology. Plug-in hybrid cars refers to fully electric operation capability, and then range extender on when additional flexibility is required. So when you want to travel further than you usually travel. So the DLR experience on this technology or on this concept of plug-in hybrid electric, there have been 4 projects that up till now, from 2019 or 2018, basically up till now, which are all finished and have interesting results in them. With starting, so in the early phases, when the concept emerged, it was 2018, 2019. It was a light conceptual study focusing on commuter fleet operation and efficiency, a collaboration project between the DLR and Bauhaus Luftfahrt, also a research entity in Germany. Then 2 projects, so one large Horizon 2020 project, IMUTEP, from 2020 to 2024. So this year it finished. It was a huge consortium with industry and universities and different research entities, like the DLR, ONERA, AIT, ILOT, and so on. And we had also the authorities there, EASA and Eurocontrol. So which were discussing also certification aspects and operation aspects for such a concept. Then there's also a TELEM LUFO project. It's basically a German funded project, and it was together with MTU and Rolls-Royce Electric on also focusing on the detailed propulsion component design, integration, and the certification aspect. Both of these had similar focus. And then there is EXACT, which is a large DLR internal project with 20 DLR institutes involved and over 100 people active. And the EXACT 1, now EXACT 2 is even larger than this, but the results are presenting on the EXACT 1 project. And it focused on global fleet simulation, the operating cost assessment of different concepts, so not just the plug-in hybrid, but also on different other concepts, and comparison between the concepts in the same framework. So I'll start with the motivation for using batteries as a primary power provider, or maybe just a thought on the project. Concluding thought would be that before 2020, this was more of a concept with a lot of uncertainties, and during these many projects or high, so not too many projects, but a lot of effort that went into the project, into the modeling of the aircraft and the project. A lot of uncertainties were already removed, so the concept is much more mature as a concept, and it seems to be a feasible one. So a lot of research is still needed, but it's not just a crazy idea that might work. It's something that needs more exploration. So why use batteries as a primary power provider? So if you're looking to plug in to shaft efficiency, so we have the sustainable energy sources, and we have on the one side, and we have the propulsor shaft energy, so which drives the aircraft basically, a propeller or a fan. It needs to be powered by these sources somehow. So what are the options? So these sources provide electricity, and this electricity can be used for different things. For example, battery production, liquid hydrogen production, synthetic kerosene production. And if we take 1 kilowatt hour for each, we'll see what's left when we get to the propulsor shaft energy. So first, on the synthetic kerosene production part, we have electrolysis, CO2 capturing, synthesis, logistics, and so on. So after the production process, what's left of this 1 kilowatt hour is maybe half that is fueled in the aircraft tank. Hydrogen looks a bit better because there's still only electrolysis and liquefaction, and then also distribution storage. But overall, you get to higher. You're able to concentrate more of this output energy into the aircraft tank. And then we have the batteries, which are quite efficient in terms of production and recycling and charging. So what you left in the tank is most of what you've, or in the aircraft storage system is most of what you've taken from the plug. And this is the plane with the energy stored in the vehicle. So further, we need to convert this energy into useful power or useful energy for the propulsion, for the aircraft propulsion. So if you take the kerosene, usually you drive a gas turbine, and it has an efficiency between 30 and 55%, depending on the class and the maturity or the how modern it is, the entry into service level. And what you're left basically from this 1 kilowatt hour is less than a quarter of the energy can be used for aircraft propulsion. For hydrogen, it's a bit better. A gas turbine and fuel cells are two options, at least more mature fuel cells. So for kerosene, you can also use fuel cells, but more high temperature ones that allow efficient reforming. But this is a really technology that needs a lot of maturing before it can be considered. So for hydrogen, we can use fuel cells much more easily, and gas turbines are even a little bit more efficient than the kerosene gas turbines, which has been explored also in Exact and in other projects as well, or potentially more efficient. So this needs to be consolidated. But overall, what's left after this whole process of converting it to storage energy and then to propulsor shaft power, we're left with about 20 to 40% of the whole energy. And for batteries, it's simply much less. There are simply much less losses in the whole process. So it's the most direct way. You're left with about 85% of the energy that you take from a flat plug. All of this is a rough estimation. It's not something that I can say this scientifically sound, but it's more for orientation. So the tendency is batteries are most efficient from sustainable sources to the propulsor shaft energy. And this is the main advantage. This is why it's interesting to look into them, especially in the context of sustainability. When we look into the limitations, so there is this one limitation actually, that it's the basically been the showstopper up till even today for industry to pick up battery as energy storage option is because of the energy density of batteries. So you look into this diagram, you can see the gravimetric energy density on the x-axis and the volumetric energy density on the y-axis. So basically, anything that's outwards on the diagonal is good. Anything inwards is bad. So batteries are really bad when it comes to energy density. So it's in fact 2 orders of magnitude, or one to 2 orders of magnitude worse than chemical energy storage in terms of energy density. And the main impact of this property is on the achievable range of battery-driven vehicles. So in order to elaborate on this, I will go into theory of range calculation, or the basic theory of range calculation for aircraft, just to explain what how the aircraft design transitions from gas turbine based to battery based. So if we look into an aircraft with the forces acting in level flight, you have thrust, drag, lift, and weight. And the aircraft wants to cover distance from A to B. So in cruise, it will have lift equals weight and thrust equals drag. This is the most basic state, which is common for aircraft, because aircraft are mostly in cruise, or it is the longer range ones. We have L over D is lift over drag, which can be used to derive the drag. So this is a parameter describing aerodynamic efficiency, the aerodynamic efficiency of the aircraft. It's basically a characteristic how well the aircraft is designed. So if you design an aircraft really well and fly it in its design point, then it will have a good L over D. If it's badly designed or not more designed for robustness rather than efficiency, then it will have a lower L over D. And higher L over D means less drag, lower means more drag. So how is energy calculated? So energy is, or work done by the engines, is basically thrust times distance traveled. So this is work. Work is force times distance. So thrust is force created by the engines, and then integrate over the distance, you get the energy. And thrust is basically the same as drag, so the weight of the aircraft divided by the aerodynamic efficiency. And this is distance averaged expression. So if we ignore aircraft mass changes or forces changes during the cruise, this would be the equation. So what is meant by, so from the work done by the engines means, so the output work of the engine, but the engine is fed by some kind of fuel, stored energy, and there is some efficiency for the transition between this stored energy into output work. So you take the fuel energy, burn it here, and some of it converts in work, which drives the aircraft. And the engine efficiency is basically the engine work output divided by the fuel energy consumed. Then if we look into, so if you take the engine work output, then we can calculate the fuel energy that's needed from A to B, basically by the work that needs to be done by the engines divided by the engine efficiency. It's basically the stored energy that you require for this, for moving the aircraft from A to B. So I hope this is clear enough. We have this fuel equation. It's basically the same then with the other all the parameters included, so the fuel energy needed from A to B, is basically depending on the aircraft mass. So a heavier aircraft will require proportionally more fuel energy. So then we have the L over D, so the aerodynamic efficiency. More aerodynamically efficient aircraft requires proportionally less energy. And more efficient engines reduce the energy proportionally as well. So all of these affect the fuel energy required proportionally. And this is, by the way, the base for the famous Brugge equation, which, however, additionally considers fuel burn. So the mass of the aircraft is reduced when it burns fuel from A to B. So it starts heavier and ends lighter. So this equation still needs some additional integration over the distance. And then you get the Brugge equation, but this is the base for it. So these dependencies on the overall mass, the aerodynamic efficiency, and the engine efficiency are still the same. So let's go into how aircraft mass can be estimated, rules of thumb. It can be divided into 4 parts. Yeah, so why aircraft mass? Because, as I mentioned here, these are the 3 main parameters. So I'll go on each of them separately and the theory behind it and how they can be derived. So first, starting with the mass, we have the payload mass, which is mostly a requirement for an aircraft. So it needs to be able to carry this much payload. Then we have the payload accommodation structure, which in case of the airliners, it is a fuselage with the onboard systems. So statistics show that fuselage, or at least in the regional short-range aircraft, statistics show that fuselage is approximately as heavy as the payload. So if we have 10 tons of payload, the fuselage is also 10 tons, more or less, with a deviation of plus minus 10%. So this is quite accurate. Long-range aircraft are a bit more heavier, so 1.1 or 2, but it's in the same order of magnitude. If we have, if we look into the aircraft mission components, so we have the wing, which needs to carry the aircraft. You have the engines, which makes it take off and keeps it in the air. We have stabilization surfaces and landing gears for the ground. And all of these aircraft, all of these components of the aircraft are depending on the aircraft, on the total aircraft mass. So a heavier aircraft will need bigger engines, it will need a bigger wing, bigger empennage, and landing gear, and so on. So all of these together make up statistically 27.5% of the total aircraft mass. And this is true for all airliners. And if you look into the statistics, so I didn't provide a statistic here, it's not published. It's something that I've checked in our databases and projects and so on. This ratio holds more or less. So there might be some, even the plus minus 10% might not be exactly accurate, but it's more or less what can be expected from these components to weigh on conventional build, the aircraft that has been built up till now. And then we have the energy storage or fuel, which is depends on the range of the aircraft. So longer range needs more fuel, as already shown. If we plot these relationships in here in this diagram, we have the fuel mass ratio of total aircraft mass. So at this point on the x-axis, the aircraft 10% of the aircraft is mass of the total aircraft mass is fuel. Here's 20% of the aircraft mass is fuel, and so on. So this is basically this upper portion of the aircraft. So 1 is the total aircraft mass, and it is segregated into fractions of the total mass here. So this first section is fuel, which is basically here plotted on the x-axis, so it increases further to the right. Then we have the wing engines, landing gear, and empennage, which are constant or depending on the aircraft mass. So they are always 27.5% of the total aircraft mass, or with the uncertainty, but this is more or less what you can expect. And then what's left after fuel and wing and engines and structure. So what you still need is fuselage and payload, or why the aircraft. This is why the aircraft is there. So it needs to carry a fuselage and carry some payload or passengers. And so the remaining mass after fuel and wing and engines and landing gear and so on is fuselage and payload, which are split more or less equally, as mentioned by statistical data. So if we look into the different aircraft classes or regional aircraft, smaller regional aircraft, they need less fuel fraction, fuel mass ratio, basically, because they serve the shortest routes. Then we have the short medium range aircraft like A320, for example, which then need more fuel fraction of the total mass because they also need to be able to serve longer distances. Then we also have the long range aircraft, which can get up to even more than 40% of the total mass of the aircraft is then fuel. So here the 40% means that, 50% means half of the aircraft is fuel, but long range aircraft are mostly almost there, some of them. And basically because long range aircraft have more fuel that needs to be carried, the total portion of the aircraft that is left for payload and fuselage is the least. So payload to total aircraft mass ratio, you can see that long range aircraft have something like 15 to 20% of their total mass is allocated for payload, and the remainder is fuel, fuselage, wing and engines and so on. And the regional aircraft have about 1/3 of their mass allocated for payload. So regional aircraft can carry most 1/3 of its mass is payload, and longer aircraft is 1/5 or 1/6 of its mass is payload. So longer, this is a summary of what I just said. So yes, if we get into an example, here in this table, you can see the regional, short, medium range, and long range classes, average fuel mass ratios, and then the payload mass ratio that is left according to the statistics. So one example, if you want to design an aircraft with 100 tons of total mass, then explore the mass breakdown of the different aircraft classes. So the whole aircraft is 100 tons, so total aircraft mass is 100 tons. If fuel mass ratio of 0.1 means 10 tons of these 100 tons are fuel, for short medium range 20 tons are fuel, and for long range 40 tons are fuel. Wing, engines, landing gear, and empennage are 28%, 27.5%, so 28 tons of 100 tons in all of these cases. So more or less for each class of aircraft, you get similar relationships. So if the aircraft flies on a short range or a long range, so the engines and wing and so on will remain more or less similar. Of course, it's not. It won't be the case like exactly the same, but the tendencies are important here. And then what's left for each class is the fuselage and payload. So the regional aircraft used up just 10 tons of these 100 tons on fuel, and a lot of it is left for a fuselage and payload carrying. So this a regional aircraft will be able to carry the most payload. A short range aircraft will be able to carry less payload. So, and if you want to have a 100 tons aircraft that serves long range routes, then it will only be able to carry 16 tons. So you will need to design one with a small fuselage and less passengers, because otherwise you cannot serve long range routes. You need a lot of fuel there. So this is the key point here. And example 2, now if you imagine having 10 tons of payload, fixed. So this is the requirement, not the total aircraft mass. You need to transport 10 tons of payload for different classes. So you need one time for the regional class, one time for the short, medium, and one example for the long range class. So what happens with the mass of the aircraft? So design payload is fixed. So fuselage and systems are mostly fixed. Okay, it won't be true for the long range fuselage. It will be a bit more heavy, but still the same order of magnitude. And if we fix these, and we know the other two, so wing, landing gear, and empennage and design fuel depend on the total aircraft mass. So when we apply these relationships, we get a 32 tons aircraft for the regional. So a 32-ton aircraft will be able to carry 10 tons on regional route. A short medium range aircraft will be 38 tons, so it will be heavier. So wing, engines, and so on will be heavier, and it needs more fuel. But what's surprising is that it's not proportional, but it's actually exponential, and or not exponential, but yeah, yeah. I'm not sure if it's exponential. No, I think it should be exponential. But that's not important. It's disproportional, so it increases quite fast and approaches infinity when the fuel mass ratio gets too heavy. So long range aircraft is more than 2 times heavier than is about 2 times heavier than a regional aircraft. This is the surprising effect of designing aircraft for longer ranges. So you need a lot more mass for such an aircraft to carry the same payload. Then we have the efficiency of the aircraft, second parameter. So I showed the work output of the engine and the stored energy, the relationship between the two, so how much of the stored energy can be used for useful work is what describes the engine efficiency. Engine efficiency depends on the engine technology, basically. So how much of it, what the technology is able to convert into useful output. But we can break it down further. So engine usually consists of a power provider and a thrust provider. And the power provider is typically in a turbofan case, gas turbine, which takes the fuel and converts it into power output. And this power output is then transferred to the ducted fan. So basically, which creates some thrust, which is then converted to work by moving the aircraft. So there are two conversions, actually. This is engine efficiency is one parameter, but it can be split into two, and engine efficiency basically equals power provider efficiency times the thrust provider efficiency. So this can be used as a breakdown to describe, especially when you change power providers, like from a gas turbine move to a battery or to a fuel cell, then this split helps to describe what happens. So there's some examples on different power providers and thrust providers. So you can have a turbofan will be a gas turbine driving a ducted fan. Turboprop would be a gas turbine driving an open propeller. Fuel cells powered electric propeller will basically means a fuel cell and electric motor driving a propeller. So the fuel cell converts hydrogen to and takes air from the ambient air to create electricity, which drives the electric motor and then drives the propeller. And then we have a battery. So battery, which drives the electric motor and which drives the propeller. So these are examples of how power provider and thrust provider can be split. So if you look into the power provider side, power provider efficiency, we have the gas turbines and 2040 technology Pareto front here. This is what we used in Exact as a Pareto front to calculate the aircraft performance. So we had basically different classes of the gas turbines, and larger gas turbines are more efficient than smaller gas turbines. And you can see how approximately what these classes mean. So 2025 megawatt class drives turbofans, 10 to 20 megawatt class would drive a large twin turboprop, so the same class as the turbofan. And the regional aircraft are under 5 megawatts class, basically. And yeah, fuel cell propulsion power providers are quite efficient, but mostly on the smaller classes. So we still have not much experience on what happens here, but you can see already that this high advantage is mostly in this class, in the small aircraft, because the gas turbines are getting not very good in the smaller megawatt classes. So they're quite good actually in the larger classes where the usual transonic aircraft fly. So they are comparable to actually to a fuel cell efficiency. So fuel cell do not have a lot of advantage here, but have a lot of advantage here. And we have the battery pack discharge efficiency plotted here, and you can see it's basically in a class of its own when it comes to conversion of power, which I already mentioned here. Some explanations on the axis that I've used, but this is mostly for after the presentation if you want to take this to look in the slides. So we have then the thrust providers, and I've plotted the two most common. There are others as well, but like for example, counter-rotating propellers or propeller with a stator and so on. But for this presentation, it's sufficient to just show comparison propellers and ducted fans. So you can have below is the Mach number of the aircraft, so the speed. 1 means the speed of sound, and after that it's supersonic aircraft, so Concorde, for example. But here it's around 0.8 is where the usual transonic turbofans fly. So most of today's airliners, and they use turbofans. So the thrust provider can be called a ducted fan. And the efficiency is around 70 to 75%, depending on the bypass ratio and how refined the technology is. And then we have also propellers as an alternative. So for turboprops are generally much more efficient as a thrust provider. But then again, we have the not very efficient power provider. So that's kind of a balance there. But turboprops can get to efficiencies of around 90% as a thrust provider. L over D, so aerodynamic efficiency is the third parameter. So how to describe the L over D again is lift to drag ratio, how much lift the wing generates, and versus how much drag the whole airframe and the lift generate. So higher L over D means more efficient aircraft, and less thrust is needed for an aircraft with a higher L over D. And a gliding aircraft is a good example that I find quite easy to understand as a concept. So a gliding aircraft, for example, a paper airplane, so a small airplane that you just throw. A glider with a L over D of 10 will move 10 meters forward when dropped from 1 meter height. So this is how it can, in my opinion, be best described. So you can, if you throw a paper airplane with an L over D of 10, it will move 10 meters for each meter that it drops. This is what L over D means. Here's some plot based on experience values on aircraft that we've seen in projects and on reference aircraft data that we have. Again, no guarantee that it's quite accurate, but it is roughly describes what the different classes of aircraft have. So we can start here again. Mach number is the x-axis, and the aerodynamic efficiency is on the y-axis. And we have gliders up here. They're quite slow, and they have really high aerodynamic efficiency because they don't have any propulsion on board, so they need to use the winds to stay in the air and to be really efficient. And yeah, they are really efficient. Then we have the general aviation aircraft, which is really a class that is really diverse. We have very efficient aircraft, and we have really inefficient aircraft that are simply robust and cheap. And this class includes single engine aircraft, trainers, home builds, and so on. And yeah, there are quite interesting concepts there. We have also commuter aircraft, so smaller than 19-seater airliners, basically. Then we have the regional aircraft with 100 seats, up to 100 seats, so like the ATR-72. Short, medium range aircraft, like A320, and long range aircraft A350. So what the pattern is, these are really not that good aerodynamically. And this one is really good, but because it's a higher technology, so it has really challenging range requirements as described. So having a good LOD keeps you with the total mass of the aircraft, helps you with the total mass of the aircraft. And these mostly don't care because they need to be built cheap to be competitive on the market. So they optimize for other parameters rather than LOD. And cost is more important, for example, for this kind of aircraft. So it is possible to build an aircraft here, which is on par with a long-range aircraft, but only if you need to. So nobody does anything if he doesn't need to do it. And this is an example why you don't need to do it. There is a brochure of the ATR-72 that can be found online. It shows a breakdown of the cost of the aircraft, so its average operation. And this brochure was in 2005. You can see here is ATR-72, Q400, CRJ-700. The cost of the ATR-72 is split into two parts. So this yellow part is the aircraft investment cost, and the blue part is the cash operating costs. So aircraft investment cost is what the airline has to pay to buy the aircraft, and then it basically takes a loan from a bank or whatever, and then pays it out upon its lifetime, or depending on terms. But this is what it pays per trip for the aircraft due to the buying the aircraft. And this is the other operating factors. So like fuel, engine maintenance, airframe maintenance, crew, landing and parking fees. And this is broken down. This blue part is broken down into different subparts. And this is the fuel cost. This was 2005. So fuel cost is a part of this blue curve, and aircraft cost is this whole bar here. This means 50% of the total cost depends on aircraft cost, and just 15% of total aircraft cost it depends on fuel cost. So even if you decide to build it 2 times more efficient, like LOD that is 20 something and really efficient engines and so on, then you get half of the fuel for operation and you'll save 7% of the total cost. But in order to do this, you need high-end technology and manufacturing. It will drive the aircraft cost up. So clearly optimization will go here and not here. This was before fuel, when fuel was really cheap. And a cheap aircraft because of this, and that's the reason why regional aircraft are not that efficient, is that they are more competitive when they're cheap and not when they are efficient. But this is a diagram showing basically a fuel cost plot and the same breakdown. So fuel cost is 15% of the total cost. Investment cost of the aircraft is half, and this was 2005 fuel costs, 3 cents per kilowatt hour. If the cost starts increasing, which is the case today or early in the year, I don't know what's exactly today, but I just copied the diagram. But yeah, this is more expensive in any case than what it was before. And now fuel costs it's actually about 2 times more expensive. So fuel costs are starting to be about 30% of the whole cost of the aircraft. So it starts to get more relevant. So, and you can also see the tendencies that ATR and Leonardo and so on, they're also looking into some higher, like newer technologies, newer engines, hybrid systems or whatever, and looking to this direction, and the incentive is there. And after that, you can see if it starts increasing, if it continues increasing, like going into SAF, synthetic air fuels, will be around here, or if it's an optimistic projection, then the fuel cost will almost match, or more or less match the investment costs. So from this point on, it really is worth it designing an efficient aircraft, so sacrificing some investment costs to drop down fuel costs. And if it goes into the pessimistic direction where fuel costs are really expensive, then manufacturers will or airliners will want to have more efficient aircraft. So this is a natural optimization relationship. Just like an information why we don't see this efficient aircraft.
Just a warning, Georgi, that we're at about 50 minutes, and just to give a bit of time, just so you know where we're at.
I'm almost done with the section, so we can then stop for questions. But yeah, just the examples on the Brigade range. So if we take the Brigade equation, now we see the logarithm of the Brigade here. I just rearranged it a bit, but this is the Brigade equation essentially. We have the energy density of kerosene, the aerodynamic efficiency of the aircraft, the engine efficiency of the power provider, of the whole engine, not just the power provider, so the whole engine efficiency combined, and the fuel mass fraction. So this is how much of the aircraft mass is fuel mass. And this is done the range dependency on these parameters. If we calculate a regional aircraft with an L over D of 15, so small, cheap, and robust airframe, we'll have and also turboprop efficiency of 25%, so small 80s engine gas turbines, which drive propellers, will be about this efficient. And then we have the fuel mass fraction of 10% that I showed. Then the expected range will be about 900 nautical miles, or 1,700 kilometers. If we do the same with short range, so L over D 17, so higher, turbofan efficiency is higher, and the fuel mass fraction is also higher, so the range gets a lot more, which is also typical for short range aircraft, about 3,000 nautical miles. And then if we go into the long range aircraft, then you can see higher L over D, like I showed in the diagram, higher engine efficiency, and fuel mass fraction. I forgot here, it should be 0.4. I'll correct the slides after when I distribute them. But yeah, it should be 4. And you get about 10,000 nautical miles range with this kind of parameters. Important clarification at this point. Is this how DLI Institute of System Architectures in Aeronautics calculate aircraft characteristics? The answer is no. We use complex multidisciplinary workflows with physically based models to calculate the key aircraft characteristics like mass breakdown, aerodynamics, engine maps, and different operating points, conditions, and ratings, and different aircraft configurations. So it's a really complex. It is not easy to model an aircraft, and we use also reference aircraft data for calibration of the models. We use interfaces or define interfaces for feeding back higher fidelity models with disciplinary experts in the different projects. And we optimize our models for defined parameters like cost for operational cost, like that we defined, or efficiency and so on. So second question is, why do I show these theoretical foundations if our models are much more complex? Well, generalizing with top-level parameters works well in explaining complex results in an understandable way. This is why I'm showing these. And it's important to understand which parameters drive what. And this also provides a good foundation for explaining electric aircraft modeling, which is the next section, basically, of the presentation. However, Also, it needs to be mentioned, generalizing only works well when the complex results are already produced and the uncertainties are cleared. So it's because we have a good knowledge on the data that I showed before. It can be generalized like this, but otherwise, one should really try to look into more into detail when assessing new concepts and not use simple relationship. However, these tendencies that I'll be showed in the next section are shown with these models, but they are a result of the experience that we had on the projects of this concept that we've calculated in the different projects. So it's just for your better understanding then. I think that this was more on the foundation of the theory. It's a good point to pause shortly and maybe opportunity to ask questions.
Yeah, what I'll do is I'll pause the recording for now.
Okay, so next section will be how to design a feasible battery-driven aircraft. I'll try to be a bit more quick on this section because then we have also some of the exact results. So half an hour, we'll see. Yeah. Then I showed the Brigade equation for kerosene-fueled aircraft range, and this is Brigade equation is necessary because aircraft becomes lighter during flight, so you need the integration of the distance. But for batteries, it's actually more simpler because battery flight doesn't burn fuel and the aircraft mass stays the same. So the integration is not necessary. You have all the parameters remain constant and you can simply multiply those. And we have, instead of energy density of kerosene, we have the energy density of batteries. So it's basically the same equation, but instead of the logarithm, you have just the battery mass fraction. So let's take a look at a retrofit solution. This is something that studies before have a lot of studies before in the like 2015 or even before that were done. Is a battery feasible for aircraft? So a lot of studies were on let's retrofit an aircraft. What happens? So I want to check here as well using this basic relationship. What happens if you retrofit an aircraft? A regional one. The reference, I'll use the regional parameters shown before. So L over D15, fuel mass fraction of 0.1. So they remain the same for the retrofit. So the same battery instead of fuel mass fraction. This is the simplest approach. Then we'll have also turboprop efficiency 25% and energy density of kerosene. They change. So battery and propeller efficiency are much higher, as already discussed, so 75% for total engine efficiency. And we have the energy density of batteries. This is really bad. So we have, especially in 2015 studies, which showed this initial studies, where people started looking into batteries as an option because the cars were successful. So if we took the battery density of cars, it's 80 times worse than kerosene. So the range of this one is 1,700 kilometers. And if you retrofit it with this kind of battery and don't change anything about the aircraft, well, you get a 65 kilometers of range. So that's kind of why you don't want to retrofit an aircraft with batteries. So it's not practically possible for regional or commuter aircraft or for any aircraft for this matter. You always end up with just too low ranges. So what will be design measures for this limited range? So how can you increase the range? So one of the options is increase battery mass to aircraft mass ratio. Another option is increase aeropropulsive efficiency and have lighter components on board. Some enablers are better aerodynamics, so higher aspect ratio wings and cleaner airframe design. So it increases airframe cost, of course, but now we have different optimization parameters. Slower flight speed, so match cruise speed with the best aerodynamic performance, which makes quite an impact most of the time because current aircraft tend to want to fly faster because of cost. mostly true for regional. For larger, transonic aircraft, they fly at the optimum, but battery designs should also avoid transonic designs because they are more difficult to get more efficient, especially on the propulsor side and the aerodynamics, which are limited by a transonic effect close to the speed of sound. Distributed propulsion is also one technobrick, which I won't be going into detail, but it helps with decreasing the takeoff power, so we have lighter engines. And then we have the range extender for hybridization. So one measure to increase the range and flexibility is have a range extender on board. So go first on the optimal battery mass to aircraft mass ratio. The example from before, you have 10 tons of fixed payload. Now we want to explore different battery to mass ratios. What happens to the aircraft mass with those? Well, it's the same, basically the same thing as with the long range and short range aircraft. And if you use the same empirical estimation, we'll get higher battery mass ratio means heavier aircraft. It's basically the same as for kerosene aircraft. This increases electric range. This increases the energy consumption of the electric aircraft because the heavier aircraft is the more electric energy is needed to move it forward. So it also increases costs because of the heavier airframe and engines and everything. So there need to be a compromise between two. You cannot infinitely go increase the range. And project experience shows that battery mass fractions between 25 and 30% are usually good compromise. And yeah, if we use this and resize the aircraft, now not just retrofit, but really resize the whole engines and wing and everything for a higher total mass and more battery mass fraction. If we first not change the aerodynamics, assume still 15 L/d, fuel mass fraction changes. Now we have 30% instead of 10. Turboprop efficiency changes to 75% because of the battery proportion, battery plus propeller efficiency, 75%, and we have the same energy density of battery as before, which is of the electric cars data from 2015. And then what happens is the aircraft gets heavier, 47 tons, so significantly more heavy, but the range is now not 70 kilometers or 65, but 200, which is still not sufficient for airliners, and so we need more changes. If we go into aeropropulsive efficiency estimation, it is not trivial to design the aircraft to be to have a good aerodynamic efficiency and propulsive efficiency. It's not a trivial matter. This is why I've used the data from the projects that we've done on this concept, and you can see they achieved L/Ds, and these are also have been some of these have been also proven with higher fidelity models, which compare the reference aircraft aerodynamics with the new design. So the biggest enabler is the higher aspect ratio wing mostly, and still some research is needed because aeroelastic effects and so on needs to be confirmed. But overall, these L/Ds are achievable, which confirms these tendencies here. I'll just go back a bit. So this is what can be expected, but is not built, but it can be if you really go into optimization. And what you get is too much. Is propulsive efficiency can be higher and L/D can be a bit higher if you design the aircraft accordingly to what the battery propulsion needs and optimize it for it. Then what does design from scratch actually amount to? So first the retrofit with 65 kilometers, so battery mass fraction. Then we changed the battery mass fraction to 30%, got 200 kilometers. Now we have a new design with 20 L/D of 21 and battery plus propeller efficiency of 80%, and we get 300 kilometers. So design from scratch can shift the range of a retrofit by a factor of 5, which is really needs to not be underestimated. So retrofitting for a completely new technology is not a good idea. New design is always needed for any new, radically new technology. And this is what it's possible, basically with 2015 car technology level. What is the effect of battery technology improvement? Well, before we had from cars, so 160 watt hours per kilogram energy density to 200 maybe, some occasions. So studies in 2015 to 20 assumed mostly these efficiencies. And currently, tier level 6 technologies, mostly from China, are basically showing 300 watt hours per kilogram on pack level. And next generation roadmaps expect 500 watt hours per pack level. And there are a lot of Chinese products or level or tier level 6 and up also showing this. So this is quite amazing how fast it developed. And we have so batteries of next generation are basically expect to be 3 times better than they were in 2015 studies. So what happens to a newly designed aircraft for 2040 batteries is you get not 300 but 900 kilometers of range, which is already starting to sound not bad. So not exactly what you need, but it's already at the domain of what you could use in aviation. And then important notice, this is not the effective, not the practical range. This is the total range of the aircraft. So practical range is something else. So now we go into these details. If I say electric flight distance estimated with a simple equation is 900 kilometers and with a battery mass fraction of 30%. This means that this distance is the whole flight of the aircraft. And usually the airliners have to have main mission and a reserves mission. This is important. Reserves mission needs to be about 100 nautical miles diversion and then loiter for 30 minutes. So which eats about 200 to 300 kilometers away from the battery. So basically 10% of the battery mass is only for reserves and only 20% of the battery can be used basically for 2/3 of the battery can be used for the main mission. So effective range, it drops significantly when you apply the reserves and other factors. So I've not shown everything, but this is the main effect. So why plug-in hybrid? This was the third option to increase range. And what's amazing is that you can increase the main mission range when you build a plug-in hybrid. So because the part of the battery is used for main mission and another part for reserves, if you split these two and use the battery for the main mission and use kerosene for reserves, and assume the same total fraction for the plug-in hybrid mass of 0.3, so battery plus range extender plus fuel. So fuel mass and range extender mass are about 5% of the total aircraft mass, and 25% remain for the battery. And this shifts the range from 600 to 750 kilometers, which is already quite a good improvement. So that's why plug-in hybrid propulsion is really synergetic with aircraft requirements and needs. So additional benefits of a plug-in hybrid is we have the range flexibility. So with this, you can have thousands of kilometers available for use. So it won't be really efficient there, but it will be able to fly them. And sometimes you need the flexibility to do it. So the range flexibility can also allow a lighter battery. You don't need to optimize for more range now because you can cover a lot of the market with this hybridization part. So shorter hybrid missions, for example, if your electric mission if you're able to fly 750 kilometers electrically, and you decide to fly 1,000 kilometers in a hybrid mode, then just a quarter of the mission will be with the gas turbine. And so the whole 1,000-kilometer mission is basically electric. So 75% of it's electric, so also quite efficient. And this is the reason why if you have a range extender, then you can potentially design for a smaller battery, basically, and make the whole aircraft lighter and more cost efficient. Okay, so what I think, no, I think I'll go on first for the range requirements. So what ranges are required for plug-in hybrid aircraft to make a difference globally? I like this diagram. This is basically the trip distance in kilometers spectrum for 90-seater, so commuter aircraft class, the really small ones. Data from 2018, so how they're utilized. And you can see most of them are used. So for most of the missions are basically under 200 kilometers, and 90% of the missions basically under 400 kilometers. So this class will be perfect for electrifying, right? And with plug-in hybrid, you can use this small amount of missions in a hybrid mode. And so you can still service the whole market with this aircraft, and most of your operation will be electric, which is great. And you can reduce a lot of emissions. The problem is now, so this is a plot of the global aviation from 2014. So the average distances served by the different aircraft classes. You can see the small aircraft, they tend to serve the smallest routes, so island hopping or whatever. Then the average range starts to gradually increase. And we go to here, the largest aircraft serve also the longest routes. What is the global fuel burn in 2014? It was basically, if you split it into classes, so under 100 seaters, they get 9% of the whole fuel. Global fuel is burned in this class. And for the commuter aircraft, you get 0 point something. So commuter aircraft are not exactly relevant for climate impact of global aviation, at least replacing the existing ones. The most relevance is, of course, on the larger ones, so aircrafts of 100 plus seats. And they fly a bit longer on average than just the typical regional aircraft fly. So if a technology is to be pursued as a game changer in aviation, then it needs to be able to cover this. And as I've shown, like 900 kilometers of battery range, even not a practical one, but the theoretical one, without the reserves is not enough for this sector. So the average missions are longer. And that's why you need the plug-in hybrid, because you can serve such missions efficiently with it by hybridizing part of the energy. This is another aircraft demand chart. So passenger demand connection length in kilometers. You can see it was from 2012 and a projection from 2032. This is pre-corona, but the tendency is what is important is that most of the flights are still concentrated on short missions. So this is a portion that can be realistically operated by efficient plug-in hybrid aircraft. Okay, now we get to exact, maybe a short break, and I'll try to browse through the main conclusions.
Yeah, I think you're probably good to keep going because, yeah, just want to make sure you get it all done. And I think the questions, it's questions discussing carbon pricing and I suppose what the only one question there was a bit of conversation around was why distributed propulsion versus um, just having like two propellers, if you're able.
Yeah, that's a good question, but it's not, it's another hour of presentation to
Yeah,
understand
okay.
what happens there.
So
It's
let's
just
just
in this case we have experience with this with modeled distributed propulsion versus two propellers, and you're able to to reduce takeoff power and the whole mass of the aircraft by distributing, because you're more redundant in case of failure. This is the basic effect, but then there are a lot of other effects that pile up and make it more efficient.
Okay, we'll leave that to a different presentation, so you can continue. Yeah.
Okay. So exact. First of all, about the exact project, as I mentioned, it was concentrated on the global impact assessment of different aircraft concepts. So the goal was to look for the most appropriate aircraft technology, so propulsion technology and overall technology that can drive sustainability forward in terms of the global impact. And the capabilities are shown here. So we had the climate impact assessment capabilities, so in-flight emissions, ground-based emissions, manufacturing, and end-of-flight assessment for the climate impact. Then we have the green energy assessment. So what are the costs? What are which one can be scaled, which cannot be scaled? So how do they how much more expensive they will be compared to fossil fuel? Then we have the Future Air Traffic Demand Analysis Institute, creating fleet network optimization schemes and maintenance simulation, ground handling simulation, and so on. And we had the aircraft design. I was a work package leader for the aircraft design capabilities. We had propulsion architecture integration into the aircraft, and basically looking for the most suitable concepts. And funding volume was large for the DLR. 20 million for a DLR internal project is quite a lot, and 20 DLR institutes basically involved. So the aircraft design work package. So we needed to expand the tools and know-how to make consistent aircraft design throughout the different classes and different concepts, which was a big challenge. And we need to explore also synergies between the different propulsion types and aircraft configurations. And also the whole goal was to allocate the most efficient concepts. So we concentrated for exact one on just the two smaller classes. So the short medium range class with over 200-seater designs. And we had a regional class also just to explore solutions like the fuel cell or the battery there. Initially, the plug-in hybrid was allocated only for the regional class as an option, but then afterwards it turned out that it's actually fitting the larger class as well. So the final models also include the plug-in hybrid in the larger class. So we have the reference aircraft, basically that are used to validate the models and calibrate those. We have the baseline aircraft, so basically a conventional aircraft with conventional technology, just evolutionary advancements for 2040. We have hydrogen concepts there, and we had also the electric and hybrid electric concepts. And the focus here on this presentation is on the plug-in hybrid. So I'm not showing everything because it's quite a lot, but the results on this one are for me or of interest for this presentation currently. So the study went as follows. We have a reference aircraft with the top level aircraft requirements. So this aircraft needs to be able to fly 2,500 nautical miles. This is basically an A321neo interpretation. So it's a short medium range design range. Then we have the PAX number, the highest density, 239, then the maximum payload and so on. So takeoff field length is also a TILA. So each aircraft model needs to be able to that we used in that. So the TILAs for our designs were based on these TILAs with some changes. So one shift was a range of 1,500 nautical miles. At the beginning of the project, we wanted to explore or to give more hydrogen technology more of a chance. So look into more shorter range cases where the hydrogen tanks are not as large. Then we also have accordingly more aggressive takeoff field length of typical 2,200 meters. For the project, we used 900 meters, so more engine installed power needed because we also tend to serve more dense networks and to serve shorter routes. So these two are connected. Then we have the 250 passenger cabin. So basically a little stretch of the reference. And approach speed, yeah, it's similar with this one, but slightly higher. Then we have some technology facts, so better gas turbines, lighter fuselage, empennage, so everything accounting to evolutionary advancements to 2040. CFRP wing with foldable wingtips, for example, was also a technobrick, and bleedless system architecture. And from these redesign or boundary condition changes, then produce a turbofan model, so the exact turbofan baseline and the exact turboprop baseline, which is slower version. So the Mach number Tila is now changed and was optimized. So we got a 0.76 I presented last time. And from this model, the plug-in hybrid model was derived. So it's having the same speed as the turboprop, and battery size is optimized for cost based on the cost models that we used in exact. In the not short, but short range, sorry. And we have a fully electric flight cabin, but I already mentioned this. So this is basically the logical modeling path. So create models that can calculate these two based on these on calibration on this model with some boundary condition changes, and then this one is derived in the same matter as these two. So all three concepts were modeled consistently with respect to each other. So like aerodynamic models, structures models, engines, and so on. All of them were optimized for a global fleet operation costs, and all were compared with the same set of boundary conditions within the project. So we used the same framework to compare the three concepts. And this approach ensured consistency and comparability between the models, basically. So this is the plug-in hybrid model of 250 seats. We have 4 engines, so again, distributed propulsion, but in this case, 4 engines was the optimal solution. This is also a big discussion, so I won't start it. So, but this is optimized, so we didn't go into more engines because this was the optimal solution for this aircraft, at least at the level and the boundary condition that we had in exact 1. We're looking into it again now in exact 2. But now we have 4 6-meter propellers, and each driven by about 4 megawatt electric motor. The batteries are designed are integrated in the nacelles, and we have a 1 range extender on the outer nacelle. And this is the mass breakdown. You can take a more closer look at it later. You can see the battery mass ratio of the total mass is basically 25%. It's optimized for this model. We have an electric range of about 500 kilometers and a hybrid range of about 2,500 kilometers with a standard payload. This is an aircraft, an electric mission of the aircraft. You can see the range capability is about 50 to 60 nautical miles, about 500 kilometers. So you have just climb and then straight away descent. So this is a typical, very short range mission, short haul mission of this aircraft. So in this mission, everything is done with the battery. The gas turbine is not used for the main mission, but will be started in case reserves are needed, so in case the aircraft needs to divert. Sufficient fuel is carried in case of a diversion after the mission is needed. And 10% battery capacity remains after the mission, and 5% contingency plus sufficient energy for electric go-around. So we have similar, this is a profile of a hybrid mission. So you can see the different power providers. We have the range extender in red and the battery in yellow, and the combined power of the two. So in climb, the battery supports the gas turbine. The gas turbine is designed mostly for cruise and not so much for climb power. So any additional power that you need is given by the battery. And the fuel is burned first, so the aircraft gets lighter. And in case the range extender fails, this is also the approach that we used in Nimutep, where EASA was also on board, and we discussed the certification aspects of that. So this is theoretically doable like that, because if it fails, if this one gas turbine fails here, you can still divert, you can see from 700 nautical miles to 1000 nautical miles, so we have 300 nautical miles. This is a no, this should be a nautical mile here, because this is nautical miles, not kilometers, sorry. So you will divert about 300 nautical miles. And this makes it basically a ETOPS type of operation. Along the route, you have to be able to have a diversion airport. Yeah, I won't go into more detail. So at the end of the mission, still need to have kerosene reserves for a diversion mission, and the battery should have about 10% capacity remaining. One aspect, and I'm out of time, so I will skip that mostly, but I'll say just taxi out, takeoff, approach landing taxi, and total, and all of this off-design operation around the airport, the batteries are much more efficient than gas turbines. So this is another advantage of the concept. And you can see in this plot here the basically the design range, or the range, service range in nautical miles. You can see the mission energy here for the three concepts, and in electric operation is basically, yeah, uncontested the efficiency of the aircraft. But what's important is, even after you use the range extender, the combined missions start to get worse than a turboprop after 1000 nautical miles. So it is the most efficient one up to 1000 nautical miles. And if we have a network like that, like when most of the routes are under 1000 nautical miles, then it can be a really efficient solution and can decrease the whole energy consumption of the fleet quite significantly. Yeah, that's more or less it. These are the fleet average transport energy for the fleet model, one of the fleet models that we calculated in exact. And the plug-in hybrid can decrease the whole fleet energy by about 45% compared to a turbofan, up to the turbofan baseline, which is quite significant. And is significantly more efficient than turboprop as well. So that's it. This was in exact by far the most energy efficient concept, also with the highest potential for climate impact reduction, only matched by hydrogen aircraft. And the concept with the highest potential for operating cost reduction, especially when expensive sustainable fuels are used, because you reduce the fuel consumption of the fleet quite a lot. And if you want to know more details on the boundary conditions and the whole results, in quantitative results on the climate impact and costs, then you can visit the DLI, the exact website, and look there for some publications and so on. Or if not, you can contact me as well in this email.
Thanks, Georgi. We'll put these, I'll get the slide pack, and we'll have the recording as well, if people want to go back over this. And I think maybe we might need to get you back in again, Georgi, to go over just some of those, some of the end conclusions in a bit more detail, particularly versus other stuff. But if